Welcome. Now what we're going to do is we're going to do a quick tutorial on the one sample Z test and the one sample T test. We're going to use the same data so you can see the difference between the two. All right. So let's begin. I'm going to share my screen. And we're going to go to Excel. So here's the database. Here's the set of data that we've got. You remember I have my grad students bend spaghetti till it breaks to get some of this data. So this is one of those bending experiments. We have from years of spaghetti bending, we have good information that the mean piece of spaghetti from the population bends at about 5.38 centimeters before it breaks. The standard deviation for that is about 27 hundredths of a centimeter. Okay, so these are the population parameters, and we could compute every value of the normal distribution with these population parameters, and we can compare the mean value of our experimental group and see if our experimental group is likely to have been drawn from this population. So what I'm going to do is I'm going to take that experimental group data, I'm going to copy it, I'm going to put it into a vector, column vector, in Matlab. What do we call this? We're going to call this EXP, experimental. Okay. Now what we'll do is we're going to run a t-test. All we need to do is know the parameters. So the t-test, let's try a z-test. Let's try a z-test first, then we'll do the t-test. So this is the command, the code for the t-test. So we're going to have a hypothesis test. Okay. We're going to have the probability that we could have drawn this sample from the population at random, okay? And we have confidence interval, okay? And then we have the statistic. Okay, so this is going to give us a logical value. H is a logical value, 0 if we fail to reject the null hypothesis, 1 if we reject the null hypothesis. P is the probability that our sample here, our experimental sample, could have been drawn from the population that we've specified with those parameters at random. The confidence interval, that is in centimeters, that is the boundaries by which if our mean difference, if the population falls outside of that confidence interval, we consider that to be rejection of the null hypothesis. It's just very different from the sample mean. The distance is too far. Or if it falls, if the population mean falls towards the center, then the mean of the sampling distribution and the mean of the population are close enough that we would consider that to be just random error. Then the statistic is the actual Z statistic that we're computing in standard deviation units. And we can compare that to the critical value in the standard normal distribution. All right, and so we're going to call it a Z test. Okay, and so we're going to use our vector of data values, experimental. We're going to put in mu. I can't remember what it is anymore because I've been talking too much. 5.38. And sigma is 0.27. So we're going to say 5.38, comma, 0.27. Okay, so those are our parameters. We're going to compare the mean of this sample to the normal distribution with these parameters. And now what we have to do is say, what alpha are we going to put? What is our type 1 error rate? Well, this is bending spaghetti, right? If we were actually testing beams that were going to be put into a safety system on a car or in a space exploration vehicle, we might choose a more restrictive alpha. But for this one, I think our default of alpha is 0.05. Oops, better put it 0.05 is plenty. Okay, now we're going to do this as let's do it as a two-tail test because I don't know what's going to happen with the spaghetti. So what I'm going to do is I'm going to split this up into 2.5% in the lower tail and 2.5% in the upper tail. Okay, so what we'll do is let's do this. We can do it this way. That gives us a two-tailed test. All right. So let's go back and take a look. What we've got is H. Let's take a look at H. H is 1. So we have rejected the null hypothesis. We're going to say this is unlikely to have been drawn from that population. Okay. The probability is 2.55 times 10 to the negative 7. So about 2.5 10 millionths. Very, very, very unlikely to have occurred as a function of random chance. Okay, good. The confidence interval, 95% of the time under the null hypothesis, we would expect the mean of the population, we would expect the mean of the population that our sample was drawn from to fall between 5.65 and 5.98, okay? And ours is 5.38, see? Does not fall in that confidence interval, so therefore we reject the null hypothesis. It's very unlikely that we could have gotten this confidence interval drawing from this population, okay? And then lastly, we have a statistic. This is our Z statistic. It's the difference between 5.38 and the mean of our sample here. Let me calculate the mean. Go down to the bottom. Uh, 5.82. The difference between 5.38 and 5.82 is very large. It's several standard deviations apart, even without accounting for the sample size. So this is a significant difference that we found using a two-tailed test. If we wanted to do this as a one-tailed test, suppose we had treated this spaghetti with some sort of chemical agent that we thought would make it stiffer, right? So we think that the difference is going to be positive. Well, we can have a right tail test, okay? We can have a right tail test. If we wanted it to be negative, okay, we could have a left tail test. And in this case, if it's a left tail test, you'll notice that we failed to reject the null hypothesis because it's in the wrong tail, right? The difference is a positive difference, okay? So that's how you would do the Z-test. Very simple. Call in your vector of your sample, okay? H, hypothesis test result, 0 if we fail to reject the null hypothesis, 1 if we reject the null hypothesis. The actual probability that our sample could have been drawn from that population, which is in our case here, well, that wasn't very good. We'd have to run it again. Sorry. The confidence interval, the range of values that we'd expect, the mean of the population that this came from, 1 minus alpha % of the time, and then the actual value of the statistics. Okay, that's a Z-test using our vector of the sample vector. Okay, mu, sigma, alpha, and then whether we're doing a two-tailed test in this case or a one-tailed test, whether it's and back down here you can see we did a right tail test and we did a left tail test. Okay, that's the Z-test. Now let's just do the same thing as a t-test. Now remember, the t-test, we don't know sigma. Just put in a question mark. We don't know sigma. So what we have to do is we're going to have to use the standard deviation of the sample to represent sigma, to estimate it. Okay, so we lose a little bit of power using the t-test for this data. But let's go ahead and do it. It's exactly the same procedure. We have H, comma, P, comma, CI, comma, stat. Exactly the same structures that we're calling out before. And that's going to be equal to t-test, not z-test, but t-test. Okay. Our sample, okay, name of our sample, and then the exact same values. We got we need mu 5.38. That was mu. We don't have sigma. It will calculate it from our data, so we don't need to worry about that. We can have alpha 0.05, comma, and then we can have a two-tailed test. Okay. And so if we take a look at our data over here, the H, again, we reject the null hypothesis. Probability, no, we failed to reject the null hypothesis. What happened here? Okay, sorry, I'm back. I had to go check. The data that I put in, I didn't think had quite this large a standard deviation. So this is all correct. I did everything correctly. Go figure. So what we found was that if we look at H, we failed to reject the null hypothesis in this case, okay, because we're using the sample standard deviation to estimate the population standard deviation. The probability is about 15%, so that's much greater than alpha, right? Much greater than 0.025 in any tail. The confidence interval is between 5.19 and 6.45, and you can see that the population mean falls well within that. Okay, so we failed to reject the null hypothesis using the confidence interval. And then the T statistic is 1.5737 at 9 degrees of freedom. So that is lower than the critical value. We wanted to find the critical value. We can do the ICDF T comma 9 degrees of freedom. Oh, gotta get the probability. 0.025 comma at 9 degrees of freedom. I think that's right. Yeah. So it's 2.62. So this would have to be negative 2.62 in that tail, or it would have to be 2.26 in the negative in the left tail, or would have to be positive 2.62 in the upper tail. And you can see that this is well towards the center of the T distribution. Okay, so everything is consistent. HPCI stat, t-test, the vector that we're using as a sample, population mean, alpha, and then whether it's a one-tailed or a two-tailed test. Let's do this as a two-tailed test, and we'll do it as a right-tailed test. Okay, we're doing everything exactly the same, except for now we're going to do a right-tailed test. T, better spell it right. And we can see that the probability is much smaller now because we put all of our alpha in the right tail, but we still have not rejected the null hypothesis. And so what was puzzling me before, and why this has this weird jump in the middle of the video, is I had to say, what's the reason for that? I probably should have just stayed on and said, hey, what the heck is the reason for that? But I went and looked, and if you take a look at the standard deviation of the sample, okay, 0.8842. This is a very large standard deviation. If you remember, if I go backwards here, the population standard deviation was 0.27. The one we calculated here, let's just do it in Excel speak, okay? Just so you can see, okay, what just happened. Yes, sorry. That's what I missed. 0.88. So this is such a much less precise than, by just random chance, than the population. And so by using this, the sample standard deviation to estimate the population standard deviation, we're really overestimating the standard error, okay, the real standard error. And so we're actually committing a type 2 error here if these were the actual population parameters. But remember, the t-test, we don't know that. We don't know that value. And so we have to use this as our best guess. And so we to make up for that, we want to take larger samples so that we, by the law of large numbers, that these start to conform to the population parameters. Okay. T-test, Z-test, I think that's it. Wow, that's easy. Oh, there's a couple other things that we could do. You know, obviously we can do a histogram, or we can do a box plot. Shoot, we've got an X box plot, and we can do a box plot. Okay, and we can start to take. What is it? There we go. We can take a look at the box plot here and see where is 5.38, right? Well, 5.38 is down here, you know, below the first percentile, right? But it's not way down in the tail. So we can take a look at our data very nicely that way using a box plot. Okay, that's the last thing I wanted to show you. I'm going to get back and back to meeting. Okay, stop sharing, and have a nice day. I never know how to end these things.